Okay, so my name is Viktor Leis. I'm from the Technical University of Munich, and I even have two talks for you, not just one. And so the first talk is on query optimization, and the second part of the talk will be on how to build a very fast query engine by compiling SQL queries basically to machine code through LLVM, which is like a compiler framework. But let's first start with query optimization. So on a very high level, query optimization is this box here, right? So you get a SQL query in, and as a result, you get a query plan out, right? And in this example, this query has basically two joins between three tables, and what the query optimizer then, its main task kind of is to decide the order of the joins and also the join method, right? In PostGIS, for instance, you have sort merge join, you have hash join, you have nested loop join, right? And so, for a lot of people, this is basically a black box, right? Because query optimizers often work well, and sometimes they don't, and understanding why they don't is actually pretty difficult, because these are very complicated pieces of software that have kind of a lot of complicated parts there. And so, the goal of this work is kind of to understand query optimization better, right? And so we'll be comparing also different query optimizers from different systems with PostGIS and see kind of if a query is slow, what are the reasons for that, right? And more specifically here in this main big box of query optimization, three main smaller components are actually also shown. Here you see one important box is cardinality estimation, because in order for the query optimizer to decide which join order is best, the query optimizer needs to know, for instance, what is or it needs to know an estimate, how large is the result of the join R join S, right, the first two. Maybe it would have been better to start with R join T, and this decision is basically to be done only correctly, basically, if you know the approximate result sizes there. So this is a kind of very important box, and most of the time here I'll be talking about this box. But there's also the cost model, which then, based on these estimates, gives you kind of like a fake time, like how long will it actually take, as opposed to just the number of rows. And then finally, you have this plan space enumeration that kind of enumerates lots of different join orders, and then picks based on the cost model the best one. So, right? So this is a very high level, and we'll look kind of into these boxes in detail. And specifically, what I kind of the questions that I want to answer here is basically how good are cardinality estimators, right? And as I said, I'll be comparing different systems here, because you can kind of do that in a pretty fair way. Including PostGIS and some commercial systems. And the second question will be, when do these, if the cardinality estimates are not so great, when do they actually lead to bad plans? Because not always do they lead to bad plans. And we'll also look at like the second box here, how important is the cost model. And the third box, for lack of time, because I have a second talk for you also in one slot, so that I will skip, so I won't talk about plan space enumeration mostly. Right? Okay, before we can actually show like the real results here, I need to talk a little bit of what we actually done, which workload and data set we've been working on. So, because I'm from academia, basically we don't actually have our own like customer with its own workload, so we have to like, usually people use like standard benchmark like TPCH. And it turns out that these standard benchmarks are actually not very good benchmark kind of for the kind of questions that we're asking, because these benchmarks are synthetic benchmarks that are kind of created through pretty simplistic data patterns, right? Everything is independent, nothing is correlated, so this is not really a challenge for query optimizers. And therefore what we've done for this work, we basically created our own benchmark, which we call join order benchmark, to answer exactly the question that we saw before. And as the foundation of that, we're using the IMDb data set from, some of you may know the website, so it's a publicly available data set, and it's about 4 gigabytes, 21 tables, so it's a pretty small data set, but for our purposes that's big enough basically. And that also allows us to run a lot of queries. And it has all kinds of information about movies and actors and all kinds of related facts, right? And it's publicly available, that's also kind of important. And the most important thing is, in contrast to the synthetic standard benchmarks, it's much more realistic because it's real world, right? So it has a lot of correlations and so on, and we'll see that. So unfortunately, we don't have like actual queries as part of the workload. We only have the data from that. So we had to make up our own query set, and we tried to make kind of, in overall, we made up like 113 queries, right? And since here we're kind of focusing on join ordering, which is maybe the hardest problem in query optimization, these queries are like structurally very simple, so it's just a select from where, right? But the main difficulty is here basically the joins here, right? And the structure of all queries is exactly this. It's just a bunch of inner joins and a couple of selections, right? And here's just the join graph, right? And so on average, our queries have about 8 joins. So this is kind of, the number of joins is not too small, but yeah. And as you see, so this is the join graph for this query. Basically, each edge is like one of these, would be one where clause here that combines 2 tables, which I've skipped, right? And you can imagine there's a lot of different join orders if you have this join graph. That there's a lot of possibilities that a query optimizer can has basically. Okay, I have one final like piece of information about like the methodology, and then we get some results finally. Since we want to, in the first step, kind of look at the different cardinality estimates of different systems, we need to kind of extract them, right? And basically what we did is for a couple of different systems, we did all these 4 steps. So we first loaded just this IMDb dataset into the database. Then we ran the default statistics tool like Analyze in PostGIS. And then, that's kind of the important step number 3, for each of these 113 queries, we looked at each intermediate result of each query, right? And that's a lot more than these 100, because for instance, our query that we saw before, it had like 8 joins, so there's like probably tens of thousands of intermediate results. For instance, if you have this join R join S.T, you have R join S, that's one intermediate result, S join T, that's also an intermediate result, and for larger join queries, you have like a huge number of these intermediate results. And for each of those, we asked the database systems, okay, what is your estimate for that result size? Right? And PostGIS, you can do that just with running the query with explain, and then PostGIS will tell you, I think the result size is 10,000, right? And in addition, what we also did, we basically actually ran each of those queries and with a select count star query, right, step 4. So basically what this gives us, like a big data set of cardinality estimates and the true value, right? And now we can kind of analyze how good these estimates are then, right? Okay, so let's look at these cardinality estimates. How do they look like? And first, before we actually look at join, let's just look at like table scan plus a selection, because remember there were also like just a selection on a single table. That's also what the database needs to, as a very first step, estimate. And here you just have a table of like these 5 systems that we measured. So we had PostGIS actually 9.4. We have 3 major commercial systems, and we have our own database system, Hyper, which I'll talk also about in the second part of the talk. And so here we're summarizing kind of the error by which the estimate is off from the true value, right? And you see kind of in all systems, the median is actually pretty close to 1. 1 is good. It means basically there's no error. However, if you look at like the 90th percentile, you already get some which means that 10% of all factors are kind of more than a factor of 2 off, right, in PostGIS. And then if you look at more extreme parts, you have like larger factors, right? And so it basically says, okay, sometimes in particular, like if you look at the max, that's kind of the worst of these, all the data that we had, you sometimes have like large errors, right? But usually they're pretty okay. I mean, they're not as terrible as we will see in a second, right? So this is not really the main problem. What is more interesting now, if we now look at joins, right? So let's first look at PostGIS only, and then we also look at the other systems. So let me explain a little bit what you see in this graph. So this graph summarizes close to 100,000 data points, right? Remember, we have these 100 queries and all these intermediate results of each query, and now we group them by a number of joins, right? So 0 means just the base table selection that we just saw in the table. 1 means 1 join, 2 joins, and so on, right? And that's what you see on the horizontal axis. On the vertical axis, you see again, the factor by which you're off, right? And here we actually distinguish between overestimation and underestimation, right? So this gray line, if you see it in the middle, that's kind of there, that's where you want to be, right? Turns out, and we show kind of one box plot for summarizing all these results for that size. And turns out what you see here is actually, you're not very close to this gray line because this is a log scale. So this is a logarithmic scale. So for instance, this means a factor of 100 off. So not 10% off, a factor of 100 off. And for instance here, what you see is, for instance, with 3 joints, PostGIS is off by a factor of 100 in more than 25% of the cases. Yeah. Okay, thanks. Yeah, thanks. I can also use the, right. Is it working? Yeah, okay. So here you see kind of, this point means that in 25% of the, more than 25% of the cases, you're off by a factor of 100, right? So these are much larger factors than we just saw before. And so there's 2 main messages here. First, the width of the box, if you see it, it gets larger with each additional join. And this is log scale again, so it gets exponentially larger. There's also like theoretical arguments why that is the case, but you can also see it empirically here. And the second thing is you have the systematic trend for underestimation. So it's much more likely that the estimate is lower than the true value than it's higher. That can also happen, as you see these bars sometimes also go up, but usually it's underestimation that's the problem. Okay, so I don't want to bash on PostGIS here because this is a PostGIS conference, so let's look at the other systems, right? Because they are actually not really better, right? That's a short message here. So we see these 3 commercial systems here, and again, our hyper system from TUM Munich. And a couple of things maybe. So I would say PostGIS, DBMS, C, and hyper actually have a kind of a similar pattern, right? If you would agree. System B is kind of terrible, just as a look of it. And DBMS A looks a little bit better than the other systems, right? However, the only thing that really looks better at them is not so much the width of the boxes, but it's just that they are kind of closer to this one line, right? If you see there, and so it turns out what they are doing is actually they kind of empirically figured out exactly this effect that we're seeing, and they have like fudge factors where they see, okay, with each additional join, you believe less in this independence assumptions that the other systems are doing, right? And it might be a good idea, at least from our data, it seems to be, leads to better results here, right? But the main message is not so much that system A is better. The main message, they are all terrible, right? But because it's still log scale. So the range that we're seeing here is just that the estimates are off like by huge factors. And we're not talking about, again, 10%, but we're talking about a factor of 100 all the time, right? Like, so, yeah, that's pretty like sobering if you think about it. Now, it still doesn't mean that you get bad plans all the time, right? Because this is just, maybe these errors cancel out, or maybe they're systematically all in the same trend, so it doesn't really matter, right? So the second question that we want to answer here is, okay, when do these estimation errors actually result in bad plans, right? Because that's what the user is interested, right? He doesn't care about these estimators, estimations, because he usually doesn't see them at all, right? But what matters is query performance, right? And to do this, we kind of did something. Our goal was kind of to figure out what would be the optimal query performance, right? If we had the optimal estimator, which always gets the right value. And for that, we actually hacked PostGIS so you can actually inject cardinality estimates from other systems, or also even the true value, right? So now, basically, PostGIS, we changed it for our data set so it has actually the true values. And this way we can run each query twice, once with its own estimates and once with the true value. And that gives us kind of the difference or the performance loss from bad estimates, right? And this is basically then summarizing the distribution, this figure A. how much worse you are because of cardinality estimates, right? So these kind of the buckets. So this bucket is like 10% off, so that's pretty good, right? You're close to the optimum. And the red ones are kind of factor of 10 off, or even more than the factor of 100 off, right? So the red bars those are really big problems, because those are basically mean that sometimes, because of these cardinality estimates, your query is like more than an order of magnitude or 2 orders of magnitude slower than it could be, right? And in fact, it's even worse, because this last bucket here, greater than 100, actually those queries never finished. Basically, we timed. I mean, they timed out. Basically, we gave them a very big limit, and so then we thought, oh, so what's happening here, right? So we looked at the query plans. Why do these queries not finish, right? What can happen? And the answer was PostGIS decided to do a nested loop join, right? And it chose a nested loop join because the estimator told it that one of the join input sizes is 1. And guess what? It turns out sometimes it's not 1 by 10,000, right? And if you then join some larger table with 1 with 10,000, you suddenly have an n-square algorithm, which kind of for larger data sets basically doesn't finish, right? And so I would say this is unfortunate for that reason, because it's kind of a self-inflicted wound, because actually it's pretty easy to fix that problem, right? Because this nested loop join, there's basically almost no upside in comparison with a hash join. Maybe you're 10% faster in the best case, but in the worst case, the query never finishes it. So this is actually kind of a decision that I would not really do as a database system, because kind of the risk-reward trade-off is not good, right? I would argue, at least. And actually, I kind of, because of this issue, I even started like a discussion of PG hackers, and I think people mostly agreed. It's just still hasn't been like changed, right? In PostGIS, yes, because they have actually a setting where you can disable nested loop joins, but that will also disable index nested loop joins. And that's too much, right? You actually only want to disable those nested loop joins where kind of both sides are don't have an index below them, right? Because this is kind of the case that's easy that's very dangerous and has little upside, let's say, right? So, but this is why we kind of again hacked PostGIS. This is this figure B. If we kind of manually did that, we disabled these kind of joins, then you see the distribution gets better, right? It gets moved to the left a little bit, and these timeouts become a lot less frequent. And then we looked at those couple remaining slow queries, and what we saw here, that was actually very interesting, because what we saw here, it's kind of a similar situation that, again, due to these systematic underestimates, and a join result was estimated to be small, and it turned out to be in reality to be larger, but in that case, PostGIS chose a hash join, and in the version that we were using, it actually also used the estimates to size the hash table. So the hash table had got a lot more hash collisions than necessary, right? And interestingly, in version 9.5, they actually fixed that. So they actually now dynamically rehash the hash table. So if they see exactly that situation, they just dynamically resize the hash table, and that basically fixes this issue. And this is also, as far as I know, it's been merged in 9.5, right? So in our version, we kind of backported that patch to make it work. So now if you look at this final distribution C after these two kind of pretty small changes, this distribution actually not so bad, right? Before, kind of a slide before, we saw these factor of 1,000 off in cardinality estimates, but now suddenly it looks like it's actually very unlikely that these bad estimates actually result in bad plans, right? So how does that even make sense, right? These two observations. And we were kind of trying to understand this for a while, and we didn't really see what's going on until we tried some other thing. Namely, so these numbers that you see here, this is basically, we only enabled primary key indexes. So we just, basically these queries in the end mostly did full table scans and hash joins, right? Now, if you add more indexes, then at least for me, kind of things made more sense, right? So this figure A is right, the same one as in C that we just saw before, and now the only thing that we add primary key indexes. And now it's a bit, you have to be a bit careful for interpreting what you see in B. It doesn't mean that adding indexes makes your query slower. It just means you're further off from the optimum. Because having more indexes basically gives you a lot more options and gives you a lot, it's much easier to not find kind of the optimal plan, right? Because it becomes like a very, very difficult maze that you have to figure out. And basically, the more like physical access paths you have, the more difficult the job of the query optimizer becomes, right? But still, it doesn't mean that it's terrible, because there's actually no timeouts here. It's just that the factor that you're off from the optimum it becomes larger, right? And this is not something the user actually usually will see, that adding an indexes makes, on average, query slower, right? It's just like a theoretical observation that the more indexes you have, the less likely you will get the optimal plan, right? So are there any questions on that? Sorry, I didn't say that you can interrupt me at any moment. Because, yeah, so that was kind of the on cardinality estimation. So let's look at the cost model, right? And what is the cost model? I mean, some of you may know, PostGIS has these 5 parameters that you can set. You have like CPU cost, you have like I/O cost, random and sequential I/O cost, and like a couple of others. I think they have 5 parameters, right? And in total, they have a pretty complex cost model, because they try to model like different kinds of joins and different kinds of access patterns. And the question is, I mean, how much impact does that have, right? And to see that, we kind of what we did here is basically we ran again our query set. And we also got the runtime from that, and we also asked PostGIS, okay, what is your estimate for the cost of that query? Or just the total query result, right? And on the top left in that figure, it's just the default PostGIS cost model, and so on the 2 axes you see the estimated cost from PostGIS, and you see the actual runtime. So ideally, you would have like a very close correlation here. I mean, you have some correlation here, but it's not that great, right? In the top left figure, right? So the big thing that would make your correlation very good is if you had the true cardinalities. This is again our like theoretical experiment here. If we inject the true cardinalities here in the lower left, then actually this correlation is very good, right? I mean, you don't have that in reality, because this is just like a theoretical thing. So this is kind of the first column here, and the other 2 columns are. Then we kind of tweaked the cost model a little, right? We thought, okay, can we make this correlation better by having different cost models? Or so this is kind of the second column. There we actually changed the relative cost of CPU and I/O. We made IU look cheaper, because here because it's 4 GB data set, it actually fits in RAM. So this actually like logically makes sense. And if you look at the second row here, it doesn't really change that much. You actually get some points down below there, right? But this is just kind of pure luck. PostGIS gets actually quick plans, but this is just by luck, right? And then the final column here, which is labeled here simple cost model, is basically where we ask the question, okay, do you even need that complicated cost model, right? And basically we replaced PostGIS cost model, which is like a 5,000 line C code, right, by like 20 lines of code, right, which is very trivial. Cost model basically just counts the number of rows that flow the results. And turns out, I mean, it's almost as good basically as the other ones, right? Because the main message here is actually because the errors from the cardinality estimates are so much larger than the ones introduced by the cost model that it's kind of overwhelmed by that, right? And the big difference is always kind of between this and not between the different cost models, right?
Would the simpler cost model not be as effective with a simpler join?
I think it doesn't really matter. I mean, it's the other way around. I think, as far as I understand. Basically, if you have more join variants, then the cost model also needs to decide between those. And a simpler model would actually kind of wouldn't know the difference between sort merge and hash join, maybe, right? So, but yeah, I mean, the main point here is not so much that the cost model doesn't matter. It's more like, even though it almost looks like on this figure, the bigger point is more that the cardinalities are much more important, right? So. Okay, so let me summarize this, and then we'll talk about kind of the second part of the talk. So the main take-home message is kind of that cardinality estimates are really, really bad for all tested systems, right? So again, I have to say that vertical axis was a log scale, right? So you have like huge errors all the time. Nested loop joins can be dangerous, right? And this seems like something that should be fixed, in my opinion. And what we also saw is that if you have more indexes, then it becomes more difficult to get to the optimal plan. It doesn't mean that the plans get worse in terms of overall performance, it just means that the job becomes harder to for the optimizer. And we also saw that the cost model is less important than the estimates, right? So if sometimes you kind of get a slow query and you kind of think, okay, let's tweak the parameters until that query is fast, right? But the trouble with that is probably some other query gets slower that you're not seeing now, because the main wave that you're swimming at is actually kind of the estimates, right? So tweaking the cost model is kind of usually not the solution. So yeah, so this is kind of the from my perspective, kind of the take-home messages here from that work, and we have a paper on that. If you Google how good are query optimizers, then you will find it, but there's also a link here. I don't know if the slides will be posted online or anything. Yeah, so do you have any questions on that part? Yeah.
So from this research, do you have any suggestions for improving the cardinality estimates? I know that's a loaded question, but.
Yeah, so the thing is, I mean, people know this, right? I mean, we're not kind of the first ones to like see this. And people have been like, in research also suggesting like for 30 years different stuff. So it seems to me that now there's a lot of different, for instance, a lot of people believe in multidimensional histograms. I'm not sure they will solve this. I don't think they will solve. They make things a little bit more difficult, a little bit better, but they also make things more complicated, right? So somebody has to decide on which columns you do these multiple dimensional. So my answer is kind of negative. I think there is no good general purpose solution that you can just implement in PostGIS and everything's much better.
You don't think join indexes would help?
Interestingly, we just had a paper on CIDR this year, right? Or yeah, in January, that basically did exactly that. So there, basically, the idea was if you join R join S, in order to estimate R join S, what you can do is you take a sample of S and look at it in the index of R. So, because that will actually give you very good estimates, right? So if you use existing index structures, and so yeah, we also have results also based on this data set, and it actually makes things significantly better, right? So if you do that, the trouble is, and probably the reason why nobody like so far has implemented that in any system that I know of, is that it's more work, right? You have to do something, and you have to have additional indexes, right? So yeah, I'm sorry, I don't have like a good solution yet, but yeah.
From your talk, you mentioned the independence assumption, and I think this, if you have a systematic underestimation, then it's quite likely that this is the cause.
Yeah, exactly. Yes, you're absolutely right. Yeah.
So that would be, you know, coming from Oracle. So this is, we have these column group statistics, which will deal with the independence assumption. As you said, it's difficult to decide which columns will actually go into that.
Yeah.
The solution Oracle proposed was to do statistics on it, so to monitor the query and see where the independence is practically breaking.
Yeah.
It does help, so.
Yeah. Can you do these column groups across tables, or is that on one table always?
It's on one table, and I know where you're heading at. That the join stuff is still not decided.
Exactly. So this is kind of also one point. The big challenge is actually join crossing correlations.
Yeah.
So across tables, you get these very large non-independent things. On one table, there's actually, if you just want to estimate the cardinality of a single table and like let's say some complicated predicates, there's these multiple the column groups as you call them. But another way to do that is actually you execute the actual query on a sample. This is actually our system is now doing that. Hyper basically, if you had a like materialized sample of let's say 1,000 rows, why not just execute those predicates on that sample? Because that will give you like, it will model everything and work beautifully, right? So
it's very, very dangerous to do that. I've seen that in practice, and you can fall into bad traps. For example, there was a life cycle model. It has a status, and the status is growing, and all statuses below the maximum are outdated.
yeah,
so
because the sample is outdated basically. Yeah.
So it's
Yeah.
like with states, they start with a 0 and
Yeah.
then 2 and 3 and it goes on. Yeah. So Oracle knows the thing called dynamic sampling. So if it doesn't know the estimate, it will take the first 30 blocks and sample what is in there.
Yeah.
And unfortunately, the version, the old versions are at the beginning of the table. Just how it works. So when they had a query that says, find me all these rows with version 0, and no, with the high version, and then it was looking at the beginning of the table and said, there is none.
Yeah, yeah.
So version is extremely good selective criteria, and it was really funny, you know. It was like, first of all, it used version. There was an index on it. It used it. Go on the index, got millions and millions, and then there was cardinality feedback kicking in. So there's a reflective part in the database that says, "Oh, you misestimated," and then do it the other way around.
Yeah.
And it did it the other way around for the next time, but after that, there was dynamic sampling kicking in. So the lab was
so you have
back and forth.
like multiple levels of cleverness, like fighting each other. Right?
Yeah.
So, yeah, I mean, I agree. I mean, actually, I also don't believe in dynamic feedback. That's also, as you said, exactly for this reason. You're kind of like jumping around in your from knowledge to ignorance, kind of, because every time you kind of have feedback. Yeah, but maybe we should. I think there was one more question, so we can get to the second part.
Okay, I have a question. You are emphasizing that with indexes, queries do not perform worse. But my question is, can the job of optimizer becomes harder? But the question is, can optimizer find better plans with indexes, or it's still?
Yeah. So the queries got. So this is why my graph was a little bit.
Okay.
You have to look at carefully, because the plans did get a lot faster. So the queries were faster if you added more indexes. It's just that you're further away from the optimal plan. Because if you have more indexes, the optimal plan is a very different one if you have no indexes, right? And so. Okay. Yeah, but I have more slides also, right? We can. Yeah. Yeah. No, this is the end of the first talk. I have a second talk, right? But yeah, it's great. So whatever, we will stop when time is out. And so the second part, I want to talk about Hyper, which you just saw, and in particular about how queries are executed in Hyper, because I think that's also interesting. There's quite some interest in PostGIS community also about compiling queries, right? And so just a few words about Hyper. So this has been like a research project from 2010, which is started by my advisor, and then I joined a little bit later. It's a relational main memory system, and it tries to be PostGIS compatible, and it's very, very fast, because it actually compiles queries to machine code, right, as opposed to like other execution engines. And it's now actually also there's been a startup, and it's been acquired and so on. But now let's talk about compilation, right? So in Hyper, basically, what happens if you get the SQL query that you see here? It's like in all systems, it's first optimized into a query plan, right? But then instead of kind of interpreting this query plan through like, let's say PostGIS would do, we actually generate code, right? On the right side here on the slide, you kind of see the code that would be generated for that query. I mean, this is the pseudocode. In reality, it's of course not pseudocode, but And here, if you assume that we're using like in-memory hash joins, then this red pipeline basically means you're scanning table R1, you apply a selection, and then you store kind of the resulting, the tuples that survive in a hash table, right? And this red pipeline, as we call it, is kind of translated to this for loop on the top right. You see it loops over all tuples in the relation, it applies selection and stores the tuple in the hash table, right? And then you kind of generate code for the next pipeline, which is the green one, which is very similar again. You scan it, put it in the hash table. And then the last pipeline, maybe the black one, this one actually is like on the probe side of the hash join, so it kind of probes into two hash tables after each other, right? So the idea here is that you kind of have tight loops over data, and where you kind of do only exactly those operations on that are in that query, right? And you generate this code that you see here at basically like a just-in-time compiler. You get a SQL query, you spit out machine code for that, right? Let's see how much time we have. It's 15 minutes, right? Yeah, so 12 minutes, okay. Then let me skip those 2 slides, maybe. So the way of course we don't compile to pseudocode because you can't execute pseudocode. Instead we compile to LLVM-IR. I don't know how many of you are aware of LLVM. So basically it's a compiler framework, an open source compiler framework. It's also used by like Clang, C++ compiler, and we're kind of hooking into like the middle end of it. So we're not compiling to C, but we're directly compiling to the internal intermediate representation, which is kind of the internal compiler representation. And you can think of it like machine-independent assembler, right? It's fairly low level, but it's machine-independent. And we don't like generate this code by printing like this language, but there's a C++ API in LLVM. There's also a C API, and so you can kind of say, you can call this library function from LLVM and we'll generate dynamically this code, and then once you generated all the code, you can just say, okay, now give me the machine code for that. And this code is kind of, we try to make it very efficient, and so for instance, like tuples are, as far as possible, within a pipeline, they are actually always kept in registers, so even machine registers. So you don't like pack and unpack tuple with each operator, but they are kind of kept in CPU registers. And that sounds very complicated, and I mean, it's not trivial. So but over time, we kind of learned how to do this more kind of from a software engineering point to make it easier to generate this kind of code, right? So because LLVM-IR is pretty low level, so what you need to build in between is some kind of abstraction layer in between, right? So LLVM doesn't even have for loops or something. It just have like basically you're jumping around in like go-tos, right? But you can build your own high-level control flow constructs, and then the code that generates machine code actually looks very similar to the code that would execute the same code, right? So you can have a for construct that starts generating this loop header and then jumps as you want it, right? And so over time, we kind of have more and more of these abstractions. We have, for instance, an abstraction for SQL value that abstracts all the null semantics, overflow checking, so that it's like one piece of code, and then the rest of the code can kind of just use this built-in library, so to speak. And the nice thing is, because we're still generating code here, all these abstractions are actually like zero cost at runtime, because you're just spitting out code there. And yeah, so, and also, not everything is code generated, but we also have like C++ stuff that is written in C++, and then both codes can call each other, right? Because we'll run in the same binary, so you have like direct interoperability between kind of this generated code and C++ code. Okay, so some performance numbers here. So this is a kind of just the first 5 TPCH number, because I just had those numbers handy. So this is in milliseconds on like a 1 gigabyte database with, set it to single threaded. And so here, these 2 columns are our hyper basically, and one says 0 and one says 01, and the difference is basically in the optimization levels of the back end, right? You can, depends, it's like a C++ compiler, right? You have different optimization settings. And I have 2 columns here. I have compilation time to generate the machine code, because that's kind of an extra phase that we have for fairness, right? Because if you generate machine code, that also takes some time. These compilers take some time, right? And then you have the actual execution time, right? But you see, I mean, that even if you add them up, right, this is a lot faster than Postgres, right? So, and it's not a surprise, right? It's you kind of generate like a very small number of instructions kind of and precisely for the query that you're executing, right? For instance, all the data type logic is kind of because the data types are known at the moment when you're compiling the query, there's no like if unnecessarily like dispatch code over different data types, right? Because it's hard baked into the machine code. And also, for instance, if you know the data type is not null, then you can get rid of the null checks at all, right? There's no null checks because you know at compile time a particular column is not null, right? So these are the kind of things that you can do directly if you compile code. Okay, so some lessons kind of that we had here from using LLVM. So LLVM is really great in almost all dimensions. It's very, very stable because it's used like in industrial strength compilers as backend. So there's very few bugs there. It's portable. It generates very efficient code. So that comes all from like being this very widely used compiler framework. I mean, the only thing that that is certainly the case is actually LLVM has non-trivial compile times. I mean, what we saw in the slide before, I think the largest compile time was what, like 100, with optimization, 150 milliseconds. But of course, it can be more if the query becomes larger, right? Because it doesn't depend on the data size, but on the query size. So if you construct crazy queries, then it will take a long time to compile, right? So this is maybe kind of the only downside by this approach. Okay, so let me just summarize the second part here, or not really summarize, but give you some hints. So we have these two papers that you see at the top. They are kind of talking specifically more about this compilation aspect in Hyper. We also have a website that has even more papers on everything else in Hyper. And this is Munich. Yeah, and everybody's looking for great people, and also we're also looking at prospective PhD students. So if you know somebody or if you would be interested, then you can get in touch with us. And I think hopefully we have some more time. Yeah, we have some time for more questions. Great. Thanks.
Did you ever think about doing your pipes in parallel? So
Yes, of course, everything is parallelized, and there's a paper on that. And that's why I made it actually single-threaded, because it would be even more unfair to Postgres. So because Postgres is just starting to parallelize, right? So not everything is parallelized there. Yeah, but exactly. So these pipelines that you saw there are actually parallelized, right? So there's a paper on that also.
Okay, again, my question. Is it correct that this compilation happens after normal optimization?
Yes, that's correct.
Okay.
So you still have the normal query optimizer, right? Spits out the plan, and then you have an additional code generation phase and an additional optimization time by the compiler, right? So this.
Am I correct assuming that the Postgres timings are on in-memory?
Yes. Yeah, exactly. So this is everything in buffer cache, right? You still have an overhead from going through the buffer cache, but it's not there was no I/O involved here, right? So this what you see is like the actual performance difference from query execution itself.
Thank you very much.
Yeah.
Have you been keeping up at all with the work that Andres Freund has been doing on JIT compilation for Postgres? Any opinions?
Yeah, basically that was my motivation of why I wanted to choose, because when we started much earlier and much more radically, right? Because Postgres cannot just rip out the query engine and it does this thing, right? So that's I mean, obviously this is I think they want to do it for aggregates and for expressions first, right? They don't want to like change all operators, because that would be much more. And yeah, obviously I think that's a good idea, right? I mean,
You did a lot of benchmarking and sort of identified some of those
yeah.
most expensive
Yeah,
areas.
yeah. I mean that makes perfect sense, right? And maybe it will be same like parallelization, that it might expand over time. And I think this makes sense, yeah, to do.
So is your basic argument that if you are quicker in optimizing the query, generating a plan, then you can check more options?
Sorry, I didn't get the.
Why would you want to make the plan generation faster? I think that the motivation is to have more time to check different options. Yeah.
Yeah, you mean like in this LVM code generation? You mean? Yeah.
Yes.
Well, if these 150 milliseconds are good enough for you, then there's no problem. Great. I mean, my only point was that maybe some people don't want to, because the query actually takes 8 milliseconds in Hyper. So it seems kind of wasteful to spend 150. Of course, you can do plan caching, you can do prepared statements and so on, right? It's just that these numbers here on the right are larger, like initial latency than you have in Postgres. Postgres doesn't have this additional machine code step, so if you have like a query that touches 10 rows, will be faster in Postgres than in our system. We're actually thinking about solving this, but it's not published yet. They will be published, also a solution for that. But I'm kind of right now focused on this query compilation problem. And also, what can happen in Hyper is if you give us a 1 megabyte SQL query, compilation will never finish. Because it will generate like, compilers are not made for computing or for compiling like insanely huge functions, right? Because you're unhappy, it will be like all in one huge function and then will never finish basically, right? So there is some additional, like, I didn't want to like just say compilation is just great, right? This is one of the things that you learn if you use it, use Hyper like over many years, right? Or use compilation for many years, yeah.
More questions? No. Let's finish.
Yeah, great.
Thank you. Thank you.